Ever wonder what really keeps a multi-ton load on a crane from just crashing to the ground? It's not just the big engine or the powerful hydraulics. In this explainer, we're pulling back the curtain on a silent hero of heavy machinery, a small, tough component that acts as the ultimate gatekeeper against gravity. Let's get into it.
All right, so here's our game plan. We'll start with the danger, what this thing actually prevents. Then we'll meet the valve itself and break down what I'm calling its 3 pillars of control. We'll find out its secret to stability, see how it acts in a total crisis, and finally, really appreciate its role as a true unseen guardian.
So to really get why this valve is so important, we have to first understand the sheer scale of the problem it's designed to solve.
I want you to picture this. A crane lifting giant steel beams hundreds of feet in the air, or a massive winch hauling a log up a steep hill. In these situations, what we call pulling loads, gravity is always fighting back, just waiting for a chance to take over. Here, control isn't just a nice-to-have, it is everything. So that begs a really important question. If the hydraulic power suddenly cuts out, what's stopping that huge weight from coming down? I'll tell you what it's not. It's not the pump, and it's not the motor. On their own, they can't hold it back. You need something else, a dedicated gatekeeper. And that gatekeeper, the hero of our story today, is this little guy, the VBCD DE A valve. On the left, you see the actual component, just a solid block of steel. And on the right, that's the engineer's view, the hydraulic schematic. This is known as a double overcenter valve, and its entire reason for existing is to tame those dangerous, overrunning loads we were just talking about. So what exactly is an overcenter valve? Well, you can think of it like a really smart, automated traffic cop for hydraulic fluid. It's designed to do 2 things and do them perfectly. Control the movement of an actuator, like a hydraulic motor, and then, crucially, lock it in place so gravity can't win. And let me tell you, these things are built tough. The body is zinc-plated steel, but the guts, the internal parts, are hardened and ground steel. They're designed to handle up to 350 bar, that's over 5,000 psi, and they do it all with basically 0 leakage. They have to be this tough, because in the jobs they do, failure is simply not an option. So how does it actually work? Well, the genius of this valve can really be broken down into 3 core jobs. Let's call them the 3 pillars of control.
Those 3 pillars are load holding, which is all about locking things down. Then there's load control, which is about making sure every movement is smooth. And finally, load safety, which is the ultimate failsafe. These 3 things together create a complete system of command over that load.
The first pillar is load holding. This one is simple but absolutely critical. When an operator lets go of the controls and that main valve goes into neutral, this valve acts like a deadbolt. It locks the actuator solid, preventing any drift or slow creep from the weight of the load. Next up, load control. This is the pillar that ensures everything is smooth and predictable. It's basically a brake that stops the load's weight from pulling the motor faster than the pump is supplying it with oil. This is exactly what prevents those dangerous, jerky, uncontrolled movements. And the third pillar, load safety. Think of this as the valve's role as a bodyguard. If a hydraulic hose bursts, and it happens, this valve is designed to instantly lock everything in place and prevent a catastrophe. We're going to see exactly how it does that in just a minute. Okay, let's really dig into that second pillar, load control, because this right here is the secret to stability. This is what prevents that awful chattering, that rat-tat-tat sound you hear in simpler, less sophisticated systems. The enemy here is a nasty little phenomenon called cavitation. See, when a load starts to run away from the pump, it creates a vacuum. In that vacuum, the hydraulic fluid can actually boil and form tiny vapor bubbles. When those bubbles collapse, and they do, violently, you get noise, vibration, damage, and a complete loss of control. This valve is engineered specifically to stop that from ever happening. And here is the absolute key difference. A simple check valve, it's like a light switch. It's either on or off. The load pressure forces it open, the pressure drops, it slams shut, and it just repeats that over and over. That's your chattering. But the VBCD DE A, it isn't a switch, it's a dimmer. It modulates the flow. It finely adjusts to create just enough back pressure to make sure the descent is always perfectly, totally, beautifully smooth. No chatter. The secret to that smooth control is something called the pilot ratio. The best way to think about it is like power steering in your car. A lower ratio, like 4.5 to 1, is like having really precise, responsive steering.
It gives the operator incredibly stable control for very delicate work. A higher ratio is a bit more efficient, but you lose some of that fine-tuned control. It's a critical balancing act engineers have to make between performance and stability.
Okay, now let's go back to that third pillar, load safety. Because this isn't just about things going smoothly. It's about what happens when things go catastrophically wrong.
In hydraulic safety, there's a golden rule. You have to have a margin of error. The pressure setting on this valve must be set to at least 1.3 times whatever the maximum load pressure is going to be. This isn't just a suggestion, it's a non-negotiable safety factor. It's the guarantee that the valve's internal spring will always be strong enough to slam the gate shut when it needs to. And this right here is its integrated shock function in action. Just imagine a hose bursts. In that instant, the pilot pressure holding the valve open vanishes. Poof, gone. The internal spring takes over and slams the valve shut in a fraction of a second. The actuator is immediately locked solid, and that heavy load is secured. A catastrophic drop is completely avoided. This, right here, is the valve's most vital role.
So, when you put it all together, it's unshakable load holding, it's perfectly smooth control, and it's instant fail-safe protection. You really start to see this component for what it is, a true unseen guardian. And this guardian is absolutely everywhere, hiding in plain sight. From the giant cranes that build our cities to the excavators that dig our foundations, the forklifts in every warehouse, the tractors on every farm. Pretty much anywhere a heavy load needs to be controlled and kept safe, a valve like the VBCD DE A is probably working silently in the background.
You know, one of our sources put it just perfectly. It said, these valves are used where there is vital importance in the system. It's not just another part in the machine, it's a critical component, a linchpin, that gets installed at the most important points in a hydraulic circuit.
And it kind of makes you think, doesn't it? In this world that's built and run by these incredibly powerful machines, how often do we actually stop to think about the small, unseen components, the hidden guardians that are the real masters of control, stability, and safety?